Students, now we are going to see the theorem of parallel axis and theorem of perpendicular axis. We are going to see now first the theorem of perpendicular axis. Theorem of parallel axis first, and then we are going to see the theorem of perpendicular axis. Here, the moment of inertia of the bodies having different geometrical shapes at the point of symmetry, if the axis of rotation is at the point of symmetry, then at that time their moment of inertia can be obtained by using integration. But it need not be necessary that every time the axis of rotation is at the axis of symmetry, it should be parallel to that, or it should be perpendicular, and for that purpose there is a theorem of parallel axis or principal axis. Here first, parallel or perpendicular axis. First we are going to see what is this theorem of parallel axis. In order to find out the moment of inertia of an object about a parallel axis, the two axes must be parallel to each other. Here consider a rigid body rotating about an axis. Here we want to find the moment of inertia about an axis passing through point O, that is about any axis. Now suppose MOP, this is the axis. Here that axis passes through the point O, its moment of inertia, you can say it will be equal to IO. Moment of inertia, this is one of the axes that should be passing through the center of mass. You can say it will be equal to ACB. Here another axis, this axis is passing through the center of mass, its moment of inertia is IC. That means these two axes, the axis passing through point O and axis passing through point C, here these two axes are parallel to each other. At that time we want to find the moment of inertia about an axis passing through the point O, that is IO. That is here the distance between these two parallel axes, you can see it will be equal to, suppose it is H. Now if we consider a particle having mass dm which is situated at point D here, if we draw, now see here, this is the point having mass dm which is at point D. Here this particle D is at a distance here OD. Now we have to join this OD, we can join this DC. Now we have to draw a perpendicular on OC produced, that is we have to draw CDN perpendicular to OC produced. Now this is your right angle triangle ODN. Here this point D is at a distance OD from axis passing through point O, and it is at a distance CD from axis passing through point C. Now here, as you can say, ODN is a right, we can say that here. First we want to find the moment of inertia of this point D from point O, that is IO, and it will be equal to integral OD square dm. OD is the distance from point O. IC is equal to moment of inertia of that point about an axis passing through point C. IC is equal to its distance from point D, its CD, therefore you can see it will be equal to DC square dm. That is, you know that distance into product of distance into mass. Now here, as we have seen that this ODN is a right angle triangle, then we can write OD square is equal to ODN square plus NO square. This will be OD square is equal to DN square plus NO square. We can write it as IO is equal to integral OD square dm. That means DN square plus NO square into dm. Now here NO, you can see it will be equal to OC plus CN. That means IO is equal to integral dn square, it remains as it is, dn square dm plus NO square dm. NO square, that means here you can say OC plus NC bracket square into dm. That is IO is equal to integral dn square dm plus x plus y square. That means OC square dm plus twice of OC into NC dm plus NC square dm. Here IO is equal to integral, you know that it will be dn square dm plus OC square dm plus twice of OC into NC into dm plus NC square. As you know that here NC square plus dn square, and that will be equal to DC square. NC square plus dn square, that will be equal to DC square. You can say this is also a right angle triangle. That means you can say that DC square is equal to this Cn square plus dn square. That means you can write it will be equal to dn square before that first here, before multiplying this, we can write here IO is equal to dn square plus multiplied by dn square plus NO. That means it will be OC plus NC bracket square into dm. That means dn square plus OC square plus twice of OC into NC plus NC square whole multiplied by dm. That is here dn square plus NC square, that will be equal to DC square. Therefore you can write DC square plus OC square plus twice of OC into NC, and then it will be dm. Then you can write IO is equal to DC square dm plus OC square dm plus twice of OC into NC into dm. See here. This will be here integration of DC square dm is equal to IC. Integral OC square dm, that is OC is equal to H, and integral dm is equal to capital M. If we want to write this separate term, before that see again here, in order to find out the moment of inertia of a body about any axis, there should be the two axes parallel to each other. One axis should pass into the center of mass. Here these are the two parallel axes. Moment of inertia passing through point O is IO, about C is passing through point C is IC. Here moment, this point, in order to find out this, consider a point having mass dm is situated at point D, which is at a distance OD from point O. This is at a distance CD from point C. Therefore, moment of inertia about an axis passing through point O is IO is equal to integral OD square dm. IC is equal to integral CD square dm. As you know, we have draw dn perpendicular to OC produced, and for that purpose this is a right angle triangle. Then OD, and you can write OD square is equal to AN square plus here you can write it will be equal to dn square. Here IO is equal to dn square plus NO square into dm. Here IO is equal to dn square plus NO, that means it will be OC plus NC bracket square into dm. Separate this term, that is dn square plus OC square plus twice of OC into NC plus NC square into dm. That means dn square, see here dn square plus cn square is equal to dc square, because this is also right angle triangle. Therefore dc square plus oc square plus twice of oc into nc into dm. That is integral dc square dm plus into oc square dm plus oc into dm. This we can write, it will be integration separately. Here integral oc square dm plus integral twice of oc into nc into dm. Now we can write this as IO is equal to, as you know that, what is this dc square dm? Dc square dm, that means it will be equal to IC plus integral OC that is the distance between the two parallel axes, that will be equal to h, and integral dm that is equal to capital M, total mass of the body. That means integral mh square, you can write it will be equal to integral dm is equal to, you can say, mass m into integral dm, OC square into integral dm plus 2OC, that means 2OC into NC into dm. Now here integral NC into dm is equal to 0. How this? See here, this point N is at a distance NC from point C. According to the definition of center of mass, the mass distribution is symmetric about its center of mass, and therefore you can say that the integral NC into dm is equal to 0. As integral NC into dm is equal to 0, this whole term becomes 0. As this term will be 0, our equation will be IO is equal to IC plus OC square integral dm. This is 0. Therefore, as you can say that IO is equal to IC plus integral dm is equal to capital M, and OC square is equal to h square. That means IO is equal to IC plus ms square. This is the principle of perpendicular axis. And in words, you can write, say here, what is the statement of this principle of perpendicular axis? Principle of perpendicular axis states that moment of inertia of a body about any axis is equal to the sum of its moment of inertia about a parallel axis passing through the center of mass and product of mass and square of a perpendicular distance between the two axes. This is the principle of parallel axis. If we know the moment of inertia about an axis passing through its center of mass, then we can find out the moment of inertia about any parallel axis. For that purpose, the two axes should be parallel to each other. See again here. What is this principle? Moment of inertia of a body about any axis is equal to the sum of moment of inertia about a parallel axis passing through its center of mass and product of mass and square of a perpendicular distance between the two axes. This is the principle of parallel axis. Then we are going to see the principle of perpendicular axis. Here, in order to prove this principle of perpendicular axis, here I can draw the diagram. This is x-axis, this is y-axis, this is z-axis, IZ, IY, and this will be equal to Ix. Ix, Iy and Ij be the moment of inertia about, see, Ix be the moment of inertia about x-axis, Iy be the moment of inertia about y-axis, and Iz be the moment of inertia about z-axis. Here, these three axes, they are concurrent at point O. The moment of, in order, this principle of perpendicular axis is used only for the laminar bodies. What is that laminar bodies? Such as a leaf or two-dimensional objects such as a ring, disc, and plain paper, plain sheets. For that purpose, that is, in order to find out the moment of inertia of the laminar bodies, we can use this principle of perpendicular axis. In this principle of perpendicular axis, the three axes should rotate it in such a way that they are mutually perpendicular to each other and they are concurrent at point O. Out of that, the two axes are in the plane and third axis is perpendicular to this plane. Here we have shown the two axes x and y, they are in the plane, while z is the third perpendicular axis. Ix, Iy and Iz are the moment of inertia about x, y and z axis. Now here, as in order to prove this principle, we can consider, suppose we have considered point P. this point P is at this distance. Point P is in the plane of lamina having mass dm. Now this point P, from this point P, we have to draw a perpendicular on x and y axis. Now we have drawn a perpendicular PM on x axis and PN on y axis. That means you can say that this and this point P is at a distance PM from x axis and at a distance Pn from y axis and at a distance PO from z axis. Now here this distance you can say it will be equal to y, and this distance you can say it will be equal to x. That means this point P is at a distance x from y axis, it is at a distance y from x axis, and it is at a distance of under root here x square plus y square, or under root y square plus x square from z axis. That means point P is at a distance y from x axis, at a distance from x from y axis, and at a distance under root y square plus x square from z axis. As we have said that Ix, Iy and Iz with the moment of inertia is about x, y and z axis. We want to find the moment of inertia about a perpendicular axis, that means Ij. Then here, as you know that OP square is equal to, you can write it will be equal to, from this OP square dm, it will be equal to moment of inertia about x axis, you can say it will be equal to Ix, and that Ix is equal to integral y square dm. Moment of inertia about y axis will be equal to integral x square dm. And moment of inertia about z axis, you can say it will be equal to Iz is equal to y square plus x square dm. That means here moment of inertia about z axis is equal to y square plus x square dm. We want to find the moment of inertia about that third perpendicular axis. Iz is equal to, you can see it will be equal to integral y square dm plus integral x square dm. That means Iz is equal to y square dm, and that it will be equal to Ix plus Iy. That means Iz is equal to Ix plus Iy. This is the principle of perpendicular axis. And this principle of perpendicular axis that can be used only for the laminar bodies. For that purpose here, the two axes, they are in the plane, and third is perpendicular to that plane. And what is the statement of this moment of inertia? That is the principle of perpendicular axis. Moment of inertia of a plane lamina about an axis perpendicular to its plane is equal to the sum of moment of inertia about two mutually perpendicular axes in the plane of the lamina, and they are intersecting at a point, or they are concurrent, or the three axes concurrent at point O. This is the principle of perpendicular axis. What is the statement again here? Moment of inertia of a plane lamina about an axis perpendicular to its plane is equal to the sum of its moment of inertia about two mutually perpendicular axes in the plane of the lamina and intersecting at the point where the perpendicular axis cuts the lamina, or you can say that they are concurrent at point O. This is the principle of perpendicular axis. Here, as we have seen that x and y are the two mutually perpendicular axes in the plane of the lamina, while z is the third perpendicular axis, which is here we have to find out the moment of inertia about this perpendicular axis z, and therefore we have find out that z is equal to integral y square plus x square dm. That means Iz is equal to Ix plus Iy. This is the principle of, or the theorem of perpendicular axis. Question can be asked on this topic. Sometimes question can be asked for 2 marks. That is, state the principle of parallel axis and principle of perpendicular axis. Or question can be asked, state and prove the principle of perpendicular axis, or state and prove the principle of parallel axis. These two theorems are very important while solving, in order to find out the moment of inertia about any axis, if we know the moment of inertia about another axis. That is, sometimes we have to use the principle of parallel axis, sometimes you have to use the principle of perpendicular axis, depending upon whether that axis is parallel or it may be perpendicular. Then we are going to see the concept of angular momentum. What is this angular momentum? That is denoted by L. Here, in case of translational motion, the linear momentum, that quantity we have seen, that is linear momentum P is equal to mv. In rotational motion, the analogous term related to linear momentum is called as a angular momentum, and that will be denoted by L. Here, this angular momentum is same as that of the torque, or it is the moment of linear momentum. If P be the linear momentum of the body, here you can say that the body performing a circular motion, P be the linear momentum of the body, then you can say that P is equal to, as you have seen that in vector form, P is equal to m into V. Angular momentum L is equal to, you can say it will be equal to R cross P. That is angular momentum is a product of linear momentum and the perpendicular distance from the axis of rotation. That means it will be R, where R is a position vector and P be the instantaneous linear momentum. If the particle performing or the object performing circular motion, then you can say that P be the instantaneous linear momentum. Here, then angular momentum, you can write it will be equal to L is equal to R cross P, which is a product of linear momentum and its perpendicular distance from the axis of rotation. Here, then L is equal to R cross P. As in magnitude, we can write this angular momentum L is equal to Rp sine theta. When the particle performing circular motion, at that time theta is equal to 90 degree and sine 90 is 1, therefore you can see it will be equal to L is equal to R into P. That is L is equal to, what is P? It will be mvr. This formula is very important. You have to remember this. That is angular momentum L is equal to mvr. Here, in order to solve the problems or our CET questions, it is very important where m is the mass, v be the velocity, linear velocity, r be the that it is the perpendicular distance from the axis of rotation. That will be r. Here in this way, angular momentum is analogous to linear momentum. That is P is equal to mv and angular momentum L is equal to r omega. Here also, linear momentum is analogous to angular momentum, linear velocity is analogous to angular momentum. Mass in case of translational motion, that is analogous to moment of inertia in rotational motion. That is, here mass plays a role in rotational, in translational motion. That role was played by this moment of inertia, that is I, in case of rotational motion. This is also one of the physical significance, that is mass and moment of inertia. These are analogous terms. Now we are going to find out an expression for angular momentum, that we have to prove that L is equal to I into omega. How this expression we have to prove? See here. We have considered this is a rigid body. This rigid body rotating about an axis, passing through its center. The axis of rotation passes through point O, which is perpendicular to the plane of the figure. This body rotates with a constant angular velocity omega. Here you can say that, suppose the body is to be made up of n number of particles having masses m1, m2, mn. They are at a distances r1, r2, rn from the axis of rotation, or the perpendicular distance from the axis of rotation are r1, r2, rn. Here, as you know that when the body performing uniform circular motion with constant angular velocity omega, but their linear velocities are different because the radii are different, and therefore linear velocities of these particles are that we have seen v1 is equal to r1 omega, v2 is equal to r2 omega, vn is equal to rn omega. Then linear momentum of this particle, you can say it will be equal to P1 is equal to m1 v1, that means m1 r1 omega, P2 is equal to m2 r2 omega. In this way we can find the linear momentum of these particles, that is P1 P2 Pn. And as you have seen that this angular momentum L is a product of linear momentum and a perpendicular distance from the axis of rotation, and therefore angular momentum of first particle, you can see it will be equal to P1 into R1. That means it will be equal to M1 R1 square omega. L2 is equal to M2 R2 square omega. In this way we can find the angular momentum of a particle having, that is Ln is equal to Mn Rn square omega. That is n number of particles. Here angular momentum you have to remember that angular momentum is a moment of linear momentum. It is a product of linear momentum and a perpendicular distance from the axis of rotation. As we have seen that when rigid body rotates about a fixed axis of rotation, then all of these angular momenta, they are also along the axis of rotation. That means you can say that the direction of angular momentum are we can find with the help of right hand thumb rule, and that is the angular momentum that also directed in the direction of angular velocity omega, that you have to remember here. And as we have found out the angular momentum of first particle, second particle, we can find the angular momentum of nth particle. Then angular momentum of n number of particles that can be obtained, that is L is equal to sum of angular momentum of all these particles, L1, L2 dot dot Ln. Therefore we can write it will be equal to m1 r1 square omega plus m2 r2 square omega plus dot 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 mn Rn square omega. Then we want to here take out common omega, m1 r1 square plus m2 r2 square plus dot 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 mn Rn square into omega. What is this? As you know that m1 r1 square plus m2 r2 square plus dot dot mn Rn square, that will be equal to summation I goes from 1 to n mi square, and that will be the moment of inertia of the body, and that will be equal to L is equal to I omega. This we can prove, that is angular momentum is equal to I omega. Angular momentum is equal to product of moment of inertia into angular velocity. That we have seen this expression for angular momentum, that is here L is equal to I omega. In translational motion we have seen P is equal to mv. In rotational motion we have proved that L is equal to I omega. Here from this also we can prove how mass and moment of inertia are analogous terms. On this topic question can be asked like this. You have to prove the expression for angular momentum, that is you have to prove that L is equal to I omega. In vector form you can write it will be L is equal to I cross omega. Direction of angular momentum is same as that of the angular velocity omega. Here in the next session we are going to see the conservation of angular momentum and another remaining topic.